well, let's say there could be a case where Z has, we could look at the case where Z is non-negative and bounded by some constant. And then we could go from that case to the case Z general, sigma y, Borel measurable. So this is actually how probability theory works in this type of settings, that you usually work with binary first, then finite range, then you extend to non-negative and bounded, then you leave the boundedness away, and then you leave the non-negativity away. This is the kind of demanding part, in a way that you need a bit of analysis there. How do we do it? Let's sketch. So the idea is here that we assume that we are looking at the function. Maybe let's take this default color, which has been blue. Imagine a function of, let's say, now we look at the function, assume that omega is now the real line. So we are looking at the function on the real line. And we look at a function, for example, of this form. And this is our, now if this is omega, so this would be Z of omega. And this is the real line. And what's bottom is omega. So let's write omega there. We know that in this picture, omega is the real line. But let's think about, okay, we have omega and the real line in this way. So we know how to handle things for finite range random variables. So what to do for non-finite range, like this type of function? What we are going to do is to approximate this function using something finite range. For example, we take, for here, we could split this. What we could do actually to approximate, so we could split this into intervals of this sort. And then we say we interpolate this function, let's say from the left at these points. So we could have this type of interpolation. Yep. So okay, that's so. Then this would be approximation of Z. So let's call it Z n, for example. So if we have 1 over n here as interpolation. So this would be one way to kind of say that, okay, Zn is, and this is finite range. Because from the picture, you see that there are only finitely many different values that Zn takes. So, and then we prove that, okay, each of these is behaving well and measurable in the sense. And for each of these, there exists an Fn, and we then approach Z by some limiting procedure. That's the way to do it, almost, except that there are two different ways to interpolate. This is interpolating the input space. Or discretizing, let's say discretizing the input space. And actually, the other option is to discretize the output space. So what we could also do, if you have a function of this form, let's call it Z omega, and this is omega again, and this is the real line. So what else we could discretize? We could discretize the output space. So let's say that we discretize the output space here in this way. And we say that, okay, this function is here of this value, and in this port it's that value. And then we say that we always kind of round down this function to the grid in the output space. So if the Z takes this value, so we round it down to this value. And in this way, we could take interpolate Z in this form. And this is discretizing the output space. We have two options. This is option A, this is option B. Which option should we take? We should take option B. This is the good, and this is the bad choice. Why so? Can you think of why B would be good? It's not an easy question.
You could have multiple inputs mapping to the same output.
That's a good idea, yeah. Let's say, yeah, that's, I think, the right direction. What is there with the good? So actually, it's less sensitive to the input space structure. So actually, imagine that this is not the real line anymore, but let's say it's Rn or something else. So it's more flexible to the input space because we are not touching the input space. We are only touching the output space, and we assume that the output space is going to be the real line always. But here we can assume that omega could be something more abstract. It could be kind of, yeah. Another thing is that this is kind of, time has proven that this is good. Especially time has proven that this works well with integration. So this approximation works with the Lebesgue integration, especially. And maybe if you know analysis, so this is kind of corresponding to Riemann integrals. And maybe you have learned that Riemann integrals are bad, at least in some context. Okay, of course, every mathematical thing has some good properties in some context, but the keyword Lebesgue integral that we will look later on. So this works well in this context as well, and that's why we will use this kind of discretizing the output space in what follows. Okay, we have about 5 minutes, or maybe let's say 4 minutes left. So now let's close this note, and I want to open the lecture note and place ourselves in the lecture note. As usual, we didn't have time to kind of prove everything that is proved in the lecture notes, but let's walk through where we are. We are here in lecture number 4, and we looked at the definitions. So we looked at these definitions, the sigma algebra generated by these, and then we looked at the case where we only have this one random variable, and we did this exercise here. We didn't do this one. Then, and here is the key theorem from Dup's representation theorem that says that yes, there exists this function little f, and we can represent z in this form. The proof is in the appendix, and it's based on something called monotone class theorem, how to do this one step to go from finite range into general. And that is so-called monotone class theorem, and it's in the appendix C. So we may have a little glimpse about it. If you like, you might read about it, but actually, if you know now how to prove these things for finite range variables and you understand this, so I think you are well equipped already to continue. But actually, the approximation by these finite range functions is a part of chapter 3, which we didn't have time to do on Monday's lecture. It was planned for the Monday's lecture, but actually time has shown that during the previous years, not me and not my colleagues who have lectured this, so nobody has ever had time to finish the chapter 3 in one lecture. So this part of the chapter 3 is actually what you could look. If you have a bit of time, you could have a look at this section, simple functions here. It is about these indicators, and it is about that, yes, we can write these linear combinations of indicator functions. And then here is the key lemma that tells how to do an approximation. So assume that f is a non-negative function, which is measurable. Then the claim is that there always exists a finite sequence of finite range functions such that they converge pointwise and in a monotone fashion to the function. And here is a picture made by Professor Kytelä, and it tells you how to do it. So you start with a function and you do this interpolation of the output space, and then first interpolation would be this. Then if you go denser, you have more better grid in the output space, so then your approximation looks like this, and this, and with 4. So you have, when you have a dense grid, so your approximation looks like this. So that's how you can approximate from below. And the theorem says here there's existence of these approximating finite range functions. What is important is that in the picture, what you see here in the picture, what you are approximating, this picture shows you a continuous function. Nothing needs to be continuous. This could be really nasty function, lots of discontinuities. It needs to be measurable, but nothing else. Continuity is not needed. And here is actually a precise construction how you can construct these kind of step functions and how you can do this interpolation. And they are so-called staircase functions. And with the staircase function, you can approximate a constant function. And that's why that's how you get this result about approximating by simple function. So let me recap the theorem, which we didn't have time to look at much details. The theorem is here. Pick any measurable function f. There always exists a sequence of finite range. That means simple functions increasing to the f. If you want to understand the proof and the existence of these, you need to do a bit of a reading on your own. And this section is very highly recommended here.